Okay, let's get started. All right. So as all of you know that this Friday we'll be having our exam number 1. And the syllabus for that exam number 1 will be up to op-amp. So whatever we have discussed till last lecture. So that would include voltage and current divisions, that would include ideal op-amps, that would include non-idealities in the op-amp. So the loop gain based approach that we have learned, that would definitely be part of the exam. Along with that, the frequency response of the op-amp will also be part of your exam 1. And as you have looked into a few examples in the last lecture, the only difference in analysis when you are taking into consideration the frequency response of the op-amp is that your loop gain P becomes a function of frequency. So initially what we had discussed is that your closed loop gain is A infinity divided by 1 plus 1 over T, where T is the loop gain defined as A times beta. That's the feed forward gain multiplied with the feedback gain. Now, because your feed forward gain A becomes a function of frequency, your total loop gain will also become a function of frequency. So that's the only difference you'll see in the frequency response based questions. Now, of course, we also have homework 3, which deals with these frequency responses. And it's kind of like homework number 2. Homework number 2 was to find out the loop gain and the overall closed loop gain from that the analysis that we have learned in class. And homework number 3 is an extension of that, which takes into account the frequency response of the op-amp as well. So what we are going to do is that in Wednesday's lecture, we're going to look into similar problems as homework number 3, or almost very, very similar to what we have in homework number 3, and try to solve those questions. So even though homework number 3 will be due later, that will be due next Monday. But because homework number 3 and the topics related to homework number 3 is part of the exam, in Wednesday's lecture, we are going to solve a few problems which are very similar to your homework number 3 problems, or even could be the same ones as well. So that's what we are going to do on Wednesday. But today we are going to start with the basics of diode, which will not be part of your exam 1. But later on, we'll have exam 2 and exam 3, and diodes will be part of that questions. Yeah, it's an exam review. So we'll not have any new topic on Wednesday. It's mostly about solving more questions on voltage and current divisions, as well as op-amps, non-idealities, and frequency response. So we try to cover as much as possible in terms of the review. But keep in mind that the best way to prepare for this exam is that you look into all the examples that we have studied in class, as well as the examples that are provided on the handouts, which we were not able to cover in the class, but will be part of the exam. So just look into all the examples that are provided as part of the handouts. At the same time, I've also shared a few examples of past exams. So if you look into this folder, there would be a few examples from 2019, 2020, and 2021. And you'll see that I'll probably just open one of them for now. And you'll see that it's very similar to what you have solved in the homeworks, that you solve the ideal op-amp based problem, find out A infinity, find out R in and R out, and apply the loop gain based formula. So for question number 1, you didn't need to find the loop gain or the closed loop gain, but I think for the other questions you needed to do that. So yeah, I think look into all these examples. These are also solved so that it's easier for you to follow and figure out what is going on with each of these questions. But if you follow all the examples, you'll have no problem in scoring well in the exam. All right, any other questions here? And a few more details about the exam. So it will be a 50-minute exam during the class lectures, 10:40 to 11:30 a.m. on Friday. Maximum marks, 100. There will be 4 questions, 25 marks each. And the questions could be very similar to what have been posted in the example questions and answers. You may need your calculator, so it's a good idea to bring your calculators to do some of the calculations. So please make sure you bring your calculators during the exam. And this is an open book, open notes, open digital devices. So you can take help from all the previous notes, the examples, whatever have been posted in the Canvas page, also from the internet. So you can take help from that. But I'll probably warn you that do not use ChatGPT, because ChatGPT is something that that works well when you try to get some information out of it. If you're trying to solve an exam problem, ChatGPT will not do a good job. So if you're thinking of using ChatGPT, I'll make sure that the questions are hard enough that ChatGPT cannot answer. So don't waste your time on ChatGPT, but try to spend more time on the actual examples that have been posted, and that will give you a better chance of scoring well in the exam. All right, so today we are going to start with our discussions on diodes. We'll go through very basics of diodes and then probably try to look into a few design examples as well. But diodes will not be part of your exam one. And why are we studying these kind of devices? We are studying now that we know about op-amps, we know about ideal op-amps as well as non-ideal op-amps. The next question that comes to your mind is that what is there inside the op-amp that creates all these features and all these properties of the op-amp. So we know that the op-amp will have an infinite input impedance if it is ideal. It will have a zero output impedance. Why is that? Those are the things that we'll try to learn in the next maybe 10 or 20 lectures in this course. So that's the main idea, that we take a component that you are very familiar with and we'll dig deep into it so that we know what that component, specifically the op-amp, is made of, and why does it have these properties that we have been talking about in the past few lectures. And in the process, we'll learn about diodes, we'll learn about BJTs or bipolar junction transistors, we'll learn about MOSFETs, and we'll look into all the details about these kind of devices. And in the end of the course, towards, let's say, end of November or middle of November, we'll try to solve a design problem that will teach you how to design an op-amp from scratch using, let's say, different devices like MOSFETs or BJTs, or in special cases, even diodes could be part of the design. But as we learn in the next few lectures, that diodes have very interesting properties, but there are these other devices like BJTs or MOSFETs, which are even more interesting and even more useful when you're trying to design that op-amp. But diodes gives you that basic fundamentals that, okay, this is the first electronic component that we are learning in this course, and it will give you a basic idea about what's there to come in the next two lectures. All right, so what is a diode? The diode is a two-terminal device, just like a resistor or a capacitor. But the main difference with a resistor or capacitor and a diode is that the diode is a unidirectional device. The resistor or capacitor is bidirectional. So if you are connecting, let's say, 2 points, one on the left side, one on the right side, and you connect a resistor in between. And imagine the case that you flip the resistor and you connect terminal A to the point where terminal B was connected earlier. It will result in the same thing. The resistor is a bidirectional device. It does not matter in which direction you connect the resistor. So if you have two terminals in your circuit, A and B, and you take a resistor, you connect that in between A and B, and then let's say you flip the resistor, connect this point at this here and this point over here. Nothing will change. The resistor is a bidirectional device. But on the other hand, the diode is a unidirectional device. What does it mean by when we say that the diode is unidirectional? This is the symbol of the diode. It's called a PN junction diode, and we'll get into that what is a PN junction and why do we call it a PN junction. But when you have a diode in this configuration, that the positive voltage is applied to the P side and the negative voltage is applied to the N side. So this is called forward biasing the diode. That your positive terminal is connected to P and negative terminal is connected to N. So that's an easy way to remember that the PN junction diode is forward biased when P is connected to positive and N is connected to negative. That's called forward biasing the diode. And in that case, the diode becomes a short circuit. That current can flow from left to right. But if you connect it in the opposite direction, that your P is connected to the negative voltage and N is connected to the positive voltage, in that case, the diode acts as an open circuit. So it's like a gate or a switch that works based on the polarities of the voltages that you apply on the two sides. So you have learned about mechanical switches in, let's say you know about mechanical switches from your childhood, that, okay, you turn on or turn off this switch with which you control the lights in this room, right? That's a mechanical switch. But diode is an electronic switch that depends on the polarities of the voltages on its two sides, on both sides. And you can turn off or turn on using the switching capabilities of the diode by applying the correct polarities on the two sides. So that's the property of the electronic switching. Now we'll go into the details of what is a PN junction and why, when you apply the positive voltage to the P side and apply the negative voltage to the N side, you have a forward bias diode. And if you do the vice reversa, you have a reverse bias diode. We'll get into the details of that. But I just wanted to be upfront with the applications of the diode, that this is what you eventually want to do with any diode. That you forward bias it, you get a short circuit. You reverse bias it, you get an open circuit. So that's the primary application of a diode in any circuit. Okay. Now, this can also be represented graphically in terms of the current and voltage plots. So let's say if you look into the left-hand side, let me use the pointer over here. So if you look into the left-hand side, what is being plotted on the y-axis is the current that flows through the diode, and we are calling it ID. So that's the current that flows through the diode. On the x-axis, you have VD. That's the voltage that you have on the both sides of the diode. So let's say we define this as the positive side. This is the negative side. And if you have a positive voltage across the diode, then you get a large amount of current through the diode because the diode is short, right? It's working as a switch which is closed. On the other hand, you have a non-conduction region when the diode is open circuited, which means that whatever voltage you apply across the diode, the current through the diode will be zero. That's the scenario when the diode is open circuited or reverse biased. So left-hand side, you have the forward bias condition, in which case the diode is a short. On the right-hand side, you have the reverse bias condition or non-conduction region. In that case, the diode works as an open circuit. Now, what are the different materials that you use to build semiconductors in general? It could be silicon, it could be germanium, it could be gallium arsenide. Now, it could also be gallium nitride. So I have not listed all the semiconductor materials that you have or that is being used today in industry or even in academia. But these are the most common three type of materials that are used as semiconductors today. And what are semiconductors? So when you are learning about semiconductors, the first question comes to mind is that what do we define as semiconductors? Now, semiconductors is something that has conductivity in between metals and insulators. You know that let's say wood. Wood is non-conductive, so there cannot be a lot of current flow through that. So same as plastic or bakelite. So there cannot be a lot of current flow through these materials. So these are insulators. On the other hand, copper, iron, silver, these are conducting materials. Semiconductors are something for which the conductivity is somewhere in between metals and insulators. So it conducts a little bit, but not a whole lot. Now that's a very interesting property, because by changing the conductivity, you can make a semiconductor work like a conducting material. You can also make a semiconductor work like an insulating material. So that's a very big advantage of semiconductors, that there is a way to change the conductivity as well, and it is called doping. So what does doping mean? That, okay, you have a semiconductor material, let's say you have silicon to start with, but then these will be part of your device physics classes, so we'll not go into a lot of details on that. But let's say with silicon, you just put some impurities inside silicon, and let's say these impurities are boron or any kind of phosphate or any other impurity that has. If you look into the electron or the atomic configuration of silicon, what you'll see is that one silicon atom is connected to 4 other silicon atoms on its 4 sides. So this is how silicon looks like. And this is because it has a valency of 4. that it connects with 4 other silicons on the 4 sides, and same thing happens with all other silicon atoms that you see here. So everything gets connected with 4 other silicon atoms on the 4 sides. That's how the lattice structure forms for silicon. But let's say you put a boron atom inside this structure. You put some impurities which are, let's say, of the type of a type that has, let's say, a boron atom. What will happen in this case, that if you look into again your periodic tables, that boron will have a valency of 3, just like silicon has a valency of 4. It can be conjoined with 4 other atoms on 4 sides, whereas boron will have a property that it can only conjoin with 3 other atoms. So what would that mean? That it can be connected with this silicon here, this silicon over here, maybe another silicon over here. But there is a silicon on this side which it cannot get, with which it cannot create a bond. So because of this impurity over here, what you have is the non-existent, or there should have been one bond over here, or one electron with which it will bond with one other electron of the silicon, but that is not present. So this is non-existence of an electron which should have been there if everything was ideal silicon. So this is called holes. The presence of or the absence of an electron that should have been there is called holes. So when you have an impurity which has a valency of 3, then you have these additional holes in the system, which just means absence of electrons. And this is what we'll call as p-type semiconductor. Why would you call it a p-type semiconductor? Because you have absence of one electron, right, in the entire structure. If you had all the electrons in the structure, you know from the atomic properties that the number of electrons will be same as the number of protons in the atom, and that's why the atom is neutral, electrically neutral. So number of electrons will always be same as the number of protons in the individual atoms. But if you look into the entire structure, here you have a silicon which cannot bond on the left hand side, because on the left hand side it does not have a silicon, it has a boron atom. So so for this silicon, you cannot create that bond on the left hand side. On the other hand, for this boron, you just have a valency of 3, and that's why you cannot create the bond on the right hand side. Why is it called a p-type or a positive type semiconductor? Is that because you do not have this bond, you have the absence of electron. What is absence of electron? Or when you have absence of electron, yes, question. Hole, yes. So when you have absence of electron, we call it a hole, right? That just means that the electron is not present. If the electron is not present, the overall structure, there could be one less electron in the overall structure, which just means it becomes more positive. Right? That's why it's called a p-type or a positive type semiconductor with this kind of impurities in. On the other hand, if you just assume that you take a material from group 5, let's say phosphorus, and then you put that phosphorus instead of this boron. So you again put some impurity in the device, in the entire structure, but in this case the impurity is of the reverse type. Here boron had a valency of 3. Phosphorus, or let's say arsenic, they will have a valency of 5. So they can connect with 5 other silicon atoms, but it will find only 4 around it. So in that case, if you just replace it with phosphorus, it can bond with all these 4 silicon atoms, but it has a valency of 5. So it will have one dangling extra bond, which will not be connected anymore. That's an extra electron. So in that case, it will be called an n-type semiconductor, because it will have one extra electron that is not bonded with anything or any other atom in the structure. So these are called p-type and n-type semiconductors. Now, why do you create these p-type and n-type semiconductors? Is because, as we said, that semiconductors have conductivity somewhere in the middle of metals and insulators. Now, by adding these impurities, what you are doing is that you are creating additional electrons or additional holes. Holes or electrons, they can conduct electricity. When an electron flows, you have current flow, right? That is current flow at an atomic level. When you have currents flowing through a material, it's basically electrons flowing through the material. So when you have these additional electrons or holes, there is a possibility that these electrons or holes will move from, let's say, one atom to another. There was an additional dangling bond over here. If you can make these additional dangling bonds move, you have a current flow. So the semiconductor becomes more like a conductor when you have more and more impurities like this. So that's the reason why you create these p-types or n-type semiconductors from the pure semiconductors, which are silicon, germanium, and gallium arsenide. So that's what we are discussing in the next slide, that n-type material will contain an excess of conduction band electrons. P-type materials will contain an excess of valence band holes. And creating these n-type or p-type material through doping, or this process of creating the n-type or p-type material is called doping, because you're adding some impurities in the original structure, and that's somewhat like doping, right? Now, something interesting you can think of, just as a thought process, that what if you put a p-type semiconductor and an n-type semiconductor close to each other, touching each other? This result is called a p-n junction, that you have a p-type semiconductor and an n-type semiconductor, and you just put or fuse them together. What would happen in this case? You know that the p-type semiconductor will have an abundance of holes. So when you have the p-type semiconductor, so remember that this is n-type. The example that is shown on the board right now is n-type, because you have a phosphorus which has an additional conduction band electron. So it has an additional dangling bond or an additional electron that can flow through this entire structure. So that's an n-type semiconductor. So that's the example you see on the right hand side, that on the right hand side you have this excess electrons that are shown on the right. On the left hand side you have this p-type semiconductor and you have these excess holes. Okay, so you have these positive signs that are the excess holes that can move around the structure. On the right hand side you have these negative signs, which are the excess electrons that can move around the structure. But at the same time you have these positive signs with a circle around it. What does that mean? That actually means the atom which does not move. The atom does not move inside any structure, right? The electrons or holes can move, but the atom itself does not move. Then the entire structure will be deformed. So let's say when you are sending current through a silver wire, does the wire become deformed? It can if you are sending a very high amount of current, but generally the wire does not become deformed. You do not see any mechanical deformity over there, which means that the atoms are not moving. It's just the electrons which are moving. Question? So both of them will increase conductivity. That's a good question. So why both of them will increase conductivity is that you have an additional electron over here. Now that electron can move from one place, and this is a conduction band electron, and it can move from let's say one atom to another. And if that happens, you have a current flow. On the other hand, if you have an n-type semiconductor, where you have, or on the other hand, if you have a p-type semiconductor, where you have an absence of electrons, where you have a hole, what does that mean? That it can accept an electron from something. So that can also increase the conductivity because it can accept electrons. So it can also help in moving electrons from one place to another. So whenever you have movement of electrons or holes, you have current. Both p-type and n-type semiconductors will help in the movement of electrons. One, by creating additional electrons. So here you have additional electrons in the n-type semiconductor. So this is the n-type semiconductor, and you have these additional electrons. Okay. On the p-type, you have these additional holes, which also help in conducting current, because they are the bond squared. An electron can come in and it can accept that electron. So it can also help in movement of the electron. And these are details in the device physics classes. So if any of you have taken device physics, it would these things should become very clear. Now, what are these other things that you see in the structure? What are these positive signs with a circle around it? These are actually the atoms. So when you have an electron, when you are The entire structure, the entire structure is electrically neutral. So when you're putting this electron outside and you're saying that, okay, I want to move this electron from one atom to another, the atom itself becomes positively charged. So that's why you have the positively charged atoms which cannot move, and the negatively charged electrons which can move from one place to another. But keep in mind that the entire structure is electrically neutral. You do not have any additional charge over it. It's just that you can move the electrons from one place to another, and that will create these positive and negative charges as the electron moves from one atom to another. Similar thing happens in a p-type semiconductor, where you have abundance of holes. You do not have, in these cases, these positive signs. They mean that there is a hole, or there is a dangling bond which can accept an electron. But as soon as you say that these holes can move from one atom to another, what it means is that the atoms become negatively charged. If the hole, there is, just think about the scenario when you have silicon and boron on this side and silicon on all other sides. Okay. This means that it can accept one electron over here, or there is a hole in this place. So if you it can, but it cannot. In this structure, if you count the total number of protons and electrons, they will be same, right? Because the boron atom will have the same number of protons and electrons. The silicon atom will also have the same number of protons and electrons. But what we are saying that in this structure, because this silicon atom could not bond with the boron did not have a valency of 4, the silicon atom here, which had a dangling bond, that can accept an electron. So that's the existence of hole we are talking about. That it cannot bond with the boron, but it can bond with a traveling electron. An electron, let's say, that is moving through the entire structure, it can bond with that. And as soon as you bond with this traveling electron, then let's say if we're talking about this structure, that becomes negative because it has one extra electron. So, or if you think about just this silicon, that will have one extra electron because it has bonded with a traveling electron, not with a boron atom, which had the same number of electrons and protons. So that's why in this case, what we are showing is the traveling holes and the overall atom that becomes negative, because as soon as you talk about holes and you talk about holes outside the atomic structure, the atom itself becomes negative. Similarly, if you talk about electrons over here, as soon as that electron comes out of the atomic structure and starts to travel, the atom becomes positive. But keep in mind, it's only the electrons and holes that move, not the atoms. If atoms had moved, then the structure will become deformed. So if you are putting current through a silver wire, the wire itself does not get deformed. Okay. So what are we showing in the middle? What is this depletion region that you see in the middle? This region gets created because you have these holes on the left-hand side. Let's say you have plenty of holes on the left-hand side, which also means that you have a lot of atoms, immovable atoms, which are negatively charged on the left-hand side inside the p region. Similarly, you have a lot of atoms which are positively charged on the right-hand side. So what would these positively charged atoms do? They will repel the positively charged holes on the left-hand side. So whatever holes are present inside the p region, near the p-n junction, they will be repelled towards left. Similarly, these negatively charged atoms which cannot move, they will repel the electrons on the right-hand side so that the electrons move further towards right. So you have these positively charged atoms over here which cannot move. But what they can do is that they can repel the positively charged holes further towards the left-hand side, because positive and positive will repel. If one of them cannot move, the other one will move. So that's why, because the atoms do not move, the positively charged holes move further towards left. Similarly, you have these negatively charged atoms over here on the p side. Because atoms cannot move, it will repel the negatively charged electrons further towards the right hand side. So in the middle, in this region, you will not have any electrons or holes. You just have positively and negatively charged atoms which are immovable. Even if they are positively or negatively charged, because they are not movable, they cannot create currents. That's why it's called a depletion region, that you have depleted this region of any kind of carrier that could have resulted in the conduction of current. So these are called majority carriers. So for example, when you talk about N-type semiconductors, the majority carriers are electrons because you have additional electrons. When you talk about P-type semiconductor, the majority carriers are holes because you have additional holes or an abundance of holes. In the depletion region, you will not have any kind of majority carrier. For the P-type semiconductor, the majority carriers were holes, but the holes are pushed away on the left-hand side because of the positively charged atoms in the N-type semiconductor. Similarly, the electrons in the N-type semiconductor, they are pushed away to the right-hand side because of these negatively charged atoms on the P-type semiconductor. So in the middle, near the junction, you have a depletion region where the entire region is depleted of any kind of majority carrier. And in this case, the majority carriers are the carriers that are able to carry current from one place to another. There is also a concept of minority carriers that, okay, because even in case of, let's say, pure silicon, you will have some electrons which have some amount of energy, some additional amount of energy, and they can come out of the atomic structure and move around. Okay, even in pure silicon, that can happen. Even in pure silicon, you can create some amount of holes. So these are not created because of the impurities. So the number of those electrons or holes will be very small. So there are inherent electrons and holes on both sides of the PN structure, either the P-type semiconductor or N-type semiconductor. So that's why if you look closely, there is a small negative traveling electron on the P side as well. In this figure, it's being shown as only one, but there are many positive holes that are flowing around in the P-type semiconductor. Similarly, inside the N-type, there is a small positive hole. There is only one positive hole that is flowing around. That's because of the inherent properties of the devices, that if you have energies in the electrons and holes in the inherent structure, they can go out of the atomic, or they can break the atomic bonds and they can move around the entire structure. But the number of those electrons and holes will be very small. So that's why you can still have holes in the N-type material, and you can still have electrons in the P-type material, but those will be called minority carriers. The number of them will be very, very small, usually in the range of, like, if there are 1,000 holes in the P-type structure, there would probably be one traveling electron in the P-type structure. If there are 1,000 electrons in the N-type structure which are moving, it'll probably have maybe one or two holes which are moving as well. So those are called intrinsic minority carriers. But on the other hand, by doping the P-type and N-type semiconductor, what you're trying to do is that you're trying to create these majority carriers, which will carry bulk of the current. And in the middle, it'll create this depletion region because the positively charged atoms will repel the holes towards the left, and the negatively charged atoms on the P side will repel the electrons further towards the right. So in the middle, you'll not have any majority carrier present. And that's why it's called a depletion region. Now you can operate the diode in three operating conditions. One, without any kind of bias, that is without applying any kind of positive or negative voltage on the P or N side. You can forward bias it, which we have already discussed, that connect a positive voltage to the P side, negative voltage to the N side. You can reverse bias it, which means connect a positive voltage to the N side and a negative voltage to the P side. So those are the definition of biasing a diode with no bias, forward bias, and reverse bias. So what does it do in the atomic structure when you have no bias connected to it? So let's say you just have this diode and you are not applying any voltage across it. So you just have the P-type and N-type semiconductors sitting beside each other, but you do not apply any voltage across the structure. So your diode voltage is 0 volt, and the current that flows through the diode is also 0. right? Because you're not applying any voltage, you'll not get any current. Everything is electrically neutral, even though you have electrons and holes, but there is no electric field to move those electrons and holes. Only if you apply a good amount of electric field, then the electrons and holes can move. They will not move by themselves, right? Even if they exist in the structure. Now, what will happen if you reverse bias it? And by definition, reverse bias means you'll apply a positive voltage to the N side and you'll apply a negative voltage to the P side. Okay, so negative to P, positive to N. So it's opposite to the forward bias condition, but you would apply positive to P and negative to N. In this case, you're trying to make a current flow from right to left, because on the right hand side you have connected plus, on the left hand side you have connected minus. Your right hand side is the N type region, your left hand side is the P type region. You can also draw it on the opposite direction, but it doesn't matter, it's just an example. So this is P and N, P on the left and N on the right. You can also draw N on the left and P on the right, and none of these concepts will change. But what is happening as you are reverse biasing the diode? What you are saying is that you already had this P-N junction with a depletion region in between. Now you're applying a negative voltage to the P side and a positive voltage to the N side. What we had said earlier is that because of the inherent properties of the atoms in the depletion region, let's say in the P-type semiconductor, you had these negatively charged atoms because you had an abundance of holes which are positively charged, which means the atoms themselves will be negatively charged to maintain electrical neutrality. Now, if you have these negatively charged atoms on the P side, they will repel the electrons, the majority carrier electrons inside the N-type region. So all the electrons will be pushed towards the right-hand side. Now, at the same time, you're applying a positive voltage at the N-type material. So on the farthest right corner, you have a positive voltage over here. So all these electrons which are being repelled by the depletion region, they will be collected at this positive side and that they will flow through the positive terminal of the battery, right? Because positives and negatives attract. You're pushing away all the negatives from the left-hand side to a right-hand side, and you have already connected a positive voltage on the right. Because negatives and positives will attract each other, the electrons that were being repelled towards right, they will be collected by this positive terminal of the battery. And same thing happens to the holes on the left. The holes on the left, they are being repelled by the positively charged atoms from the N-type region. They are being repelled towards the left-hand side. And on the left-hand side, you have a negative voltage. You have the negative terminal of the battery. Again, negatives and positives will attract, which means that all the holes which are being repelled towards the left-hand side, they will now be collected by the negative terminal of the battery. So electrons being repelled from the depletion region gets collected by the positive terminal of the battery. Holes being repelled from the depletion region towards left, they will be collected by the negative terminal of the battery. So what does this mean? That the depletion region becomes wider and wider, that you can push away more number of holes to the right-hand side or left-hand side and more number of electrons to the right-hand side toward the terminals of the battery, and you can keep on doing it, right? That you can push away more amount of electrons towards the right, you can push away more number of holes towards the left, and they will be collected at the battery. So in the reverse bias condition, your depletion region widens, your depletion region becomes larger and larger. This is another way of saying that you will have less amount of conductivity through the device, through the diode, when you are reverse biasing it. Why? Because we have already agreed that the current flow or the conductivity happens. When do we say that a material is conductive? When there is flow of electrons or flow of holes through the device. Inside the depletion region, there is no majority carrier electrons or majority carrier holes, right? Only if these majority carriers flow through the depletion region, you'll say that this material is conductive, right? In this case, you are widening the depletion region. You are making sure that there is no majority carrier that can make the current conduction happen. And that's how you are making sure that the device, the PN junction, becomes non-conductive. As the depletion region becomes wider and wider, You can imagine that this part is made of wood, and this part is made of, let's say, silver or iron or copper. So as you are applying more and more reverse bias to it, the region that is made of wood, that increases. So the possibility that there could be a current flow through the device, that reduces. And eventually you'll see that in the reverse bias condition, there would be, if you are applying a good enough voltage, there should not be any current flow through the device. Is this concept clear? The concept of reverse biasing and widening of the depletion region. Okay. If this is clear, then it is very easy to understand the forward bias condition. In the forward bias condition, you apply positive voltage to the P side and negative voltage to the N side. And you're trying to make current flow from left to right. Correct? So you'll apply a positive voltage, positive terminal of the battery to the P type, and negative terminal of the battery to the N type. Now remember, what this depletion region was trying to do is that it was trying to push away electrons on the right hand side and holes on the left hand side. But now, because you have connected a positive terminal of the battery, which is connected to the P, and negative terminal of the battery, which is connected to the N, what you will see is that the battery also tries to repel the holes and tries to repel the electrons on the right. So it will try to repel the holes on the left, and it will try to repel the electrons on the right. So even though the depletion region is trying to push away the electrons towards the right, the battery is preventing it. Even though the depletion region is trying to push away the holes towards the left, again, the battery is preventing it. So you cannot have a lot of holes pushed towards left, or you cannot have a lot of holes pushed towards right, or you cannot have a lot of electrons that are pushed towards right. What does that mean? That means that depletion region itself shrinks, because you cannot push away the electrons towards right and you cannot push away the holes towards left because of the existence of the battery. And if the battery is powerful enough, if the battery is more heavily, like much more powerful than the depletion region, eventually what you will see is that this region which is non-conductive, again, assume that it is made of wood, whereas this and this part is made of metal. So this part which is made of wood, that will keep on shrinking and shrinking. And at some point, when this battery is strong enough, it's as if this part which is made of wood does not exist at all. So you'll get a direct current flow from the battery to the device back to the negative terminal of the battery. So that's why in forward bias, if you are applying a high enough forward bias, there will be a current flow through the device. Okay. Questions?
So for the reverse bias,
yeah.
You like had a current meter.
You'll see zero current.
Okay, but like for the first like
yes, if you can monitor the expanding of the depletion region, that will happen in let's say nanoseconds or microseconds. So you're right, theoretically yes, that if you can monitor it for nanoseconds in the beginning, when you're just applying the negative bias or the reverse bias, you'll see that initially there will be a small amount of current flow and then it will stop. So this is how the characteristic of the diode looks like. So on the y-axis, again, you are plotting the green, the diode current, ID. So that's the diode current. And on the x-axis, you are plotting the diode voltage. So on the positive x-axis, you apply a positive bias or a forward bias. So as you see that as you are applying a high enough amount of positive bias or a forward bias, you are shrinking and shrinking the depletion region and eventually shrink it to zero. And at that point, you'll see that there is a high amount of current flow starting through the diode. So this is called the threshold voltage of the diode. That when you start seeing a high amount of current flow happening through the diode. On the other hand, if you are talking about a reverse bias region, when VD is negative, so on the negative or the left-hand side x-axis, you'll see that the amount of current is very close to zero, but it is not exactly equal to zero. And why is that? Because in any kind of device, there would be some amount of leakage. And what is the source of this leakage here? If you go back of the original scenario when you just talked about PN junction, we said that, okay, we'll apply this, when you are applying reverse bias, you'll connect the negative terminal of the battery to P and the positive terminal of the battery to N. As you apply the positive terminal of the battery to N, remember that we talked about minority carriers and not majority carriers. So these minority carriers will create some amount of leakage current through the entire structure. So again, if you go back to this reverse bias condition, think about this. You have a positive terminal of the battery connected at the N side. There is one single hole over here in this cartoon diagram. Of course, because this is cartoon diagram, I'm showing only one. There would actually be thousands, but in terms of the ratio, they will be much lower than the number of majority carriers. But as you apply this positive voltage at the N side, you have this minority carrier, you have this minority hole over here, which will be pushed towards this left-hand side. As you apply the negative terminal of the battery towards the P side, you have this minority electron over here, which will be pushed towards the right side. So because these minority carriers can still flow through the depletion region towards the other side, you'll have some amount of small leakage current, which we are showing over here. So in reverse bias condition, the current will not actually be equal to 0. It will be a very small amount, possibly nanoamperes or even picoamperes, and that amount of current will flow through the device because of the leakage. Okay, so we'll stop here and we'll continue our discussions on the diode after the exam, so next week. But on Wednesday, we'll be having an exam review, and Friday, we'll be having the actual exam one. Thanks, everyone.